chart refers to phase-to-phase voltages. To determine the correct wire size and insulation rating for the primary side of a pole-mounted transformer, consider these factors: firstly, voltage rating; secondly, ampacity; and thirdly, insulation thickness. The voltage rating of the wire should exceed the maximum phase-to-phase voltage the transformer experiences. In this scenario, the phase-to-phase voltage is 12,470 volts, thus a wire rated for at least 15 kilovolts is needed. Ampacity dictates the wire's capacity to handle the transformer's maximum load current. Calculate this current using the transformer's power rating and efficiency. Insulation thickness must adequately withstand the maximum voltage exposure. Given the 15 kilovolt requirement, the wire's insulation must be rated accordingly. Based on these considerations, a number 2 solid copper wire with 15 kilovolts insulated sheathing seems suitable. However, consulting a qualified electrician or engineer is crucial to confirm the precise wire size and insulation rating for the specific application. Let's delve deeper into each of these factors. When selecting a wire, its voltage rating is paramount. It must be capable of withstanding the maximum voltage that the wire will be exposed to in the electrical system. Exceeding this rating is a safety measure, preventing insulation breakdown and potential hazards. For a 12,470 volt system, a 15 kilovolts rating offers a sufficient margin. Ampacity, the current carrying capacity of a wire, is equally crucial. It's the maximum current, in amps, that a conductor can carry continuously without exceeding its temperature rating. Several factors influence ampacity, including wire size, insulation type, and ambient temperature. Consult appropriate ampacity tables, such as those found in the National Electrical Code, also known as NEC, to determine the correct wire size for the anticipated load. To calculate the load current, you'll need the transformer's power rating, typically expressed in kilovolt amps, also known as kvolt amps, and its efficiency expressed as a percentage. The formula to determine the primary current is as follows: primary current equals transformer kilovolt amps times 1000 divided by the square root of 3 times the primary voltage times the transformer efficiency. For instance, if the transformer is rated at 100 kilovolt amps with 95% efficiency, the primary current would be 100 kilovolt amps times 1000 divided by the square root of 3 times 12,470 volts times 0.95, which equals approximately 4.87 amps. Based on this current, you can select a wire size with an appropriate ampacity rating from the NEC tables. Insulation thickness is another critical parameter. It determines the wire's ability to withstand high voltages without insulation failure. The higher the voltage, the thicker the insulation required. For a 15 kilovolt system, the insulation must be rated for at least 15 kilovolts. Different insulation types offer varying levels of dielectric strength. Cross-linked polyethylene, also known as XLPE, and ethylene propylene rubber, also known as EPR, are common insulation materials for high-voltage applications. These materials provide excellent electrical insulation and resistance to environmental factors. Furthermore, consider the environmental conditions in which the wire will be installed. Temperature, moisture, and exposure to chemicals can all affect wire performance and lifespan. Select a wire with insulation that is suitable for the specific environment. In outdoor applications, ensure the wire is sunlight resistant and capable of withstanding temperature variations. For underground installations, use a wire specifically designed for direct burial. Proper installation practices are essential to ensure the longevity and reliability of the wiring system. Follow all applicable codes and standards, such as the NEC, and use appropriate connectors and terminations. Avoid damaging the insulation during installation, as this can compromise the wire's voltage rating. Always de-energize the circuit before working on any electrical equipment. Working on live circuits can be extremely dangerous and can result in serious injury or death. Use appropriate personal protective equipment, also known as PPE, such as insulated gloves and safety glasses. If you are not comfortable working with electricity, consult with a qualified electrician. Electrical work can be complex and dangerous, and it's always best to err on the side of caution. In addition to the factors mentioned above, consider the following when selecting wire for a transformer: primary, firstly, conductor material, secondly, stranding, and thirdly, shielding. Copper and aluminum are the most common conductor materials. Copper has higher conductivity than aluminum, but it is also more expensive. Aluminum is lighter than copper, which can be an advantage in some applications. Solid or stranded conductors are available. Solid conductors are less flexible than stranded conductors, but they are also less expensive. Stranded conductors are more flexible and easier to work with, especially in tight spaces. Shielding is used to reduce electromagnetic interference, also known as EMI. Shielded cables have a layer of conductive material around the conductors. This layer is grounded to prevent EMI from interfering with the signal. When sizing the wire, consult NEC Table 310.16 for ampacity ratings based on conductor type, insulation, and temperature rating. Adjust the ampacity rating for ambient temperature and the number of conductors in a raceway using the correction factors provided in the NEC. For instance, if the ambient temperature is higher than 30 degrees Celsius, you'll need to direct the ampacity of the wire. Similarly, if you have more than 3 current-carrying conductors in a raceway, you'll need to apply adjustment factors as per NEC Table 310.15. Remember that voltage drop is another important consideration, especially for long wire runs. Excessive voltage drop can affect the performance of the equipment connected to the circuit. To minimize voltage drop, use a larger wire size or reduce the length of the wire run. The NEC provides guidelines for voltage drop in branch circuits and feeders. Typically, a voltage drop of no more than 3% is recommended for branch circuits and no more than 5% for feeders. To calculate voltage drop, use the following formula: voltage drop equals 2 times K times L times I, divided by circular mils, where K is the constant for the conductor material, L is the length of the wire in feet, I is the current in amps, and circular mils is the area of the conductor. In summary, selecting the correct wire size and insulation rating for a transformer primary requires careful consideration of several factors, including voltage rating, ampacity, insulation thickness, environmental conditions, and applicable codes and standards. Consulting a qualified electrician or engineer is always recommended to ensure the safety and reliability of the electrical system. Always prioritize safety when working with electricity. To energize circuits, use appropriate personal protective equipment, and follow all applicable codes and standards. When in doubt, consult with a qualified electrician. The National Electrical Code, also known as NEC, provides comprehensive guidelines for electrical installations, including wire sizing and insulation requirements. Familiarize yourself with the NEC and consult it regularly to ensure compliance with the latest standards. Additionally, local codes and regulations may also apply. Check with your local authorities to ensure compliance with all applicable requirements. Regular inspection and maintenance of electrical systems are essential to ensure their continued safety and reliability. Inspect wiring for signs of damage or deterioration and replace any damaged or worn components. Test circuit breakers and ground fault circuit interrupters, also known as GFCIs, regularly to ensure they are functioning properly. Keep electrical panels clean and free of obstructions. Proper maintenance can help prevent electrical hazards and extend the life of the electrical system. Furthermore, consider surge protection for sensitive electronic equipment. Power surges can damage electronic devices and cause data loss. Surge protectors can help protect against these surges. Install surge protectors at the service entrance and at individual outlets where sensitive equipment is connected. Lightning protection is also important, especially in areas prone to lightning strikes. Lightning can cause significant damage to electrical systems and structures. Lightning protection systems can help protect against lightning strikes. These systems typically consist of lightning rods, grounding conductors, and surge protection devices. Education and training are crucial for anyone working with electricity. Participate in electrical safety training programs to learn about the hazards of electricity and how to work safely. Stay up to date on the latest codes and standards. Share your knowledge with others to promote electrical safety in your community. Electrical safety is everyone's responsibility. By following safe practices and promoting electrical safety awareness, we can help prevent electrical accidents and save lives. When dealing with high-voltage systems, it's crucial to understand the specific safety requirements and procedures. High voltage can be extremely dangerous, and even a small mistake can have serious consequences. Only qualified personnel should work on high-voltage equipment. These individuals should have extensive training and experience in high-voltage safety. Always use appropriate personal protective equipment, including insulated gloves, sleeves, and hard hats. Maintain a safe working distance from energized equipment. Use hot sticks or other insulated tools to work on high-voltage circuits. Never approach energized equipment without proper training and authorization. Follow lockout/tagout procedures to ensure that equipment is de-energized before working on it. Lockout/tagout involves disconnecting the power source and placing a lock and tag on the disconnect switch to prevent accidental energization. Inspect all equipment and tools before use to ensure they are in good working condition. Replace any damaged or worn components. Be aware of the potential for arc flash. Arc flash is a dangerous electrical explosion that can occur when a high-voltage circuit is interrupted. Arc flash can cause severe burns, blindness, and even death. Wear appropriate arc flash protective clothing when working on or near energized equipment. Follow all safety procedures and guidelines to minimize the risk of arc flash. In addition to the above, consider the following factors when working with high voltage: firstly, grounding, secondly, clearances, and thirdly, communication. Proper grounding is essential for high voltage safety. Grounding provides a path for fault current to flow back to the source, which helps to trip circuit breakers and prevent electrical shock. Ensure that all equipment is properly grounded before energizing it. Maintain adequate clearances around high-voltage equipment. Clearances are the minimum distances that must be maintained between energized equipment and other objects. These clearances are specified in the NEC and other standards. Good communication is essential for high-voltage safety. Ensure that all personnel involved in the work are aware of the potential hazards and safety procedures. Use clear and concise language to communicate instructions and warnings. Establish a communication plan before starting any work. Remember, high voltage safety is a serious matter. By following safe practices and procedures, you can minimize the risk of accidents and injuries. Never take shortcuts or compromise safety. The consequences can be devastating. Always prioritize safety and consult with qualified professionals when working with high-voltage systems. The specific recommendations provided are for general informational purposes only and do not constitute professional engineering advice. Always consult with a qualified and licensed electrical engineer or electrician for specific guidance on your project. They can assess your specific needs and requirements and provide recommendations that are tailored to your situation. Furthermore, local codes and regulations may vary. Ensure that you are familiar with and comply with all applicable codes and regulations. Failure to do so can result in fines, penalties, and other legal consequences. Electrical work can be dangerous. If you are not qualified, do not attempt to perform electrical work yourself. Hire a qualified electrician to do the work for you. This will help ensure that the work is done safely and correctly. Proper electrical design and installation are essential for the safety and reliability of any electrical system. By following safe practices and consulting with qualified professionals, you can help ensure that your electrical system is safe and efficient. And remember, always prioritize safety and never take shortcuts or compromise safety. The consequences can be devastating. The NEC, specifically Articles 250.166, 300.5 and 310.15 provide detailed guidance on grounding and bonding requirements. Also, the NEC provides comprehensive tables and examples for calculating feeder and service conductor sizes based on different load types and demand factors. Consult Chapter 9 of the NEC for detailed examples. For example, NEC Table 310.16 provides ampacity ratings for conductors based on insulation type and temperature rating. Always refer to the latest edition of the NEC for the most up-to-date requirements.